So, hello everyone. In this presentation, I'll be discussing the estimation of viscosity in molecular transport along with microscopic laws and molecular theories. So, we'll move step by step from macroscopic laws to molecular theories, then to the mixture of models, suspensions, and experimental measurement. Then, starting, we have uh, fundamental laws and nature of viscosity. As we know, viscosity is one of the most fundamental transport properties governing momentum transfer in fluids. So, it represents the internal resistance offered by a fluid to deforming under stress, specifically shear stress. In gases, we know viscosity arises mainly from molecular momentum exchange, and as for liquids, it arises due to intermolecular cohesive forces and activation energy barriers. Then, for accurate estimation of viscosity, we have multiple steps and domains, including fluid mechanics and pipe flow calculations, heat and mass transfer, as you can see. Uh, yeah. Then further moving on, we have Newton's law of viscosity. It is a basic relation that defines. Here is the relation that defines tau equals to mu times du by dy. This what this means is shear stress, that is tau, is directly proportional to velocity gradient. So to understand the derivation, we have to imagine two parallel plates. Suppose these are these two parallel plates, and we have to fix the bottom plate. Then the top plate will let us assume that it moves with velocity u, and a fluid is present in between them. So for our experiment, we would observe that the force is equally proportional to area, and force is also proportional to velocity, and force is then inversely proportional to distance. So after combining all these proportionalities and then dividing them by area, we would obtain shear stress is directly proportional to velocity gradient. Then to remove the proportionality, we have to introduce a constant that would be our viscosity. Mm. Then we have several assumptions in this. So we have to assume that it follows a continuum hypothesis, Newtonian behavior, isothermal conditions, and a laminar flow. Then we have some limitations also, that this theory is not valid for non-Newtonian fluids. Firstly, then viscosity varies with temperature and pressure, and it fails at molecular scale. Now let us move from microscopic behavior to molecular explanation.
So now we have Maxwell's molecular theory of gas viscosity. So in this, Maxwell provided the first molecular explanation of gas viscosity. He showed that viscosity arises from momentum transport by randomly moving molecules. The fundamental expression is mu is directly proportional to rho times average molecular speed times mean free path. Now let's briefly understand the derivation. Consider gas flowing in x direction and velocity varying in y direction. Molecules cross layers carrying momentum. A molecule moving from lower layer to upper layer carries lower momentum. Using Taylor's expansion for velocity difference and kinetic theory expression for molecular flux, we obtain mu equals 1/3 rho c bar lambda. After substituting expressions for mean speed and mean free path, we find viscosity increases with square root of temperature. Also, there are some critical insights that we need to remember. Gas viscosity increases with temperature, unlike liquids. Also, there are some assumptions that we need to keep in mind. First of all, the gas is dilute gas, the molecules are hard spherical molecules, and the collisions are elastic binary collisions. Next, we have the Chapman-Enskog rigorous solution. Chapman and Enskog solved the Boltzmann equation rigorously. They considered real intermolecular potentials and statistical mechanics. The viscosity expression becomes mu equals 2.67 into 10 to the power minus 6 times square root of molecular weight times temperature divided by sigma squared times collision integral. Here m is the molecular weight, T is temperature, sigma is collision diameter, and omega is the collision integral depending on intermolecular potential. The collision integral accounts for real molecular interactions. Now we see the derivation. So first of all we start from the Boltzmann equation, then we assume near equilibrium, then we expand the distribution function, linearize the collision operator and integrate to obtain the shear stress. Unlike Maxwell's simple relation, this predicts mu proportional to t to the power n, where n is between zero point 0.6 and 1. This gives much better agreement with experiments. Also, it has some limitations, like it requires tabulated collision integral values which fail near critical point. Next, we have the Sutherland equation. Sutherland equation modifies temperature dependence of viscosity. Mu over mu naught equals T over T naught to power 3 by 2 times T naught plus S divided by T plus S. This equation is semi-empirical. Sorry. Yeah. This equation is semi-empirical. It is derived by approximating the collision integral variation with temperature. Physically, it accounts for intermolecular attractive forces decreasing with temperature. Widely used in aerospace, CFD, and atmospheric modeling. But this is valid only for dilute gases and moderate temperature ranges. Next, we have the Eyring's activated rate process theory. So, Eyring showed that liquids behave differently. Molecules are closely packed. For flow to occur, molecules must overcome an energy barrier. Eyring treated viscous flow as an activated rate process. Also, from transition state theory, jump rate equals kBt over h times exponential minus activation energy over RT, where A is the pre-exponential factor, EA is the activation energy for viscous flow, R is gas constant, and T is absolute temperature. In the logarithmic form, we have ln U equals ln A plus EA by RT. This predicts a linear relationship between ln mu and 1 by T, confirmed that experimentally for many liquids over moderate temperature ranges. Higher activation energy means higher viscosity. It works well for oils and polymer melts. Also, it has some limitations. Parameters must be determined experimentally. Now, next we have the Wilk equation for mixtures. For gas mixtures, viscosity is not simple average. Wilk derived an expression accounting for molecular interactions. Mu mix equals summation of xi times mu I divided by summation of xj times phi of ij. Here xi is the mole fraction of species I, mu I is pure component viscosity, and phi ij is the interaction parameter accounting for binary molecular collision effects. It is derived by simplifying Chapman-Enskog multi-component transport equations. Also, it is applicable to natural gas processing, combustion modeling, air separation systems, and chemical reactor design. For limitations, this has mainly one limitation, that it is valid mainly for dilute gas mixtures. Now, next we have the Einstein equation for suspensions. So in this, we consider solid particles suspended in fluid. So Einstein derived that mu effective equals mu naught times 1 plus 2.5 phi, where mu effective is effective suspension viscosity, mu naught is continuous phase viscosity, and phi is particle volume fraction. Einstein derived this using Stokes flow hydrodynamics around rigid spherical particles. And also, the factor of 2.5 emerges from exact solution of Stokes equation and integration of stress distribution around the sphere. It is theoretically derived and not experimentally fitted. It is valid for very dilute suspensions, rigid spherical particles, and creeping flow. It is not valid for concentrated suspensions. Next, we have Stokes falling sphere viscometry. Now, this is an experimental method. When a sphere falls through the liquid, three forces act. These three forces are the downward weight of the sphere, the buoyancy force upward, and the viscous drag upward. At terminal velocity, all these forces balance each other. Weight equals buoyancy plus drag force. Substituting all these expressions and solving for viscosity, we get mu equals 2 times r squared g times density difference divided by 9v terminal. Here r is the sphere radius and g is the gravitational acceleration. Rho s and rho f are sphere and fluid densities, and vt is the terminal velocity. Also, this is valid only when the Reynolds number is less than zero point 0.1. It is used for measuring viscosity of oils, glycerin, and syrups. So, in conclusion, viscosity estimation depends on system type. For gases, we have Maxwell, Chapman-Enskog, and Sutherland equations. For liquids, we have Eyring equation. For mixtures, we have Welk equation. And for suspensions, we have Einstein equation. For experimental determination, we also have Stokes method. Each equation has specific assumptions and validity limits. Selecting the correct model is essential in transport phenomena and engineering design. Thank you.